Good evening everyone. My name is Renu Raman Sabu and today we will be discussing some of the assignment questions of week 11 assignment and some of the previous year questions. So now let us go to the first question. So the question is, lead is a superconducting material below 7 Kelvin and it has a critical magnetic field of 800 into 10 to the power minus 4 Tesla close to 0 Kelvin. Okay, so what is the data that has been given? So it has told about lead and it is superconducting below T is this is your critical temperature because less than this it is superconducting, more than this it is not. And critical magnetic field, so this is the maximum magnetic field you can apply uh, which will satisfy the Masonic effect. If you apply some more magnetic field, then it will again revert back to its normal state. So for lead to be superconducting, you have to apply magnetic field which is less than this critical magnetic field. So 800 into 10 to the power minus 4 Tesla, and this is your magnetic field at T close to 0 Kelvin. So this is at T0 you can consider. So this 0 represents the temperature. So now we have to find what is the critical current that flows through the long lead wire of radius 5 millimeter is closest to. So what we have to do, so let us imagine a lead wire which has a diameter which is a radius of 5 millimeter, or this is 10 millimeter of diameter. So if some current will pass through it, then there will be magnetic field around it. So at a distance r, so if at a distance r, the magnetic field will be 5 by 2 by r. So this is the relation between the current and the magnetic field strength, or if it is B, what you can write as B is equal to mu naught by 2 pi r. Okay. So at 2 Kelvin, now the question is, this will be the current that will pass if a magnetic field of B is there. Okay, the radius r we know, so for the radius r we have to put the radius which is that of the lead wire. So r we have to put 5 millimeter. Mu naught we know, the current we have to find, and the magnetic field, this should correspond to critical magnetic field at 2 Kelvin. So we know the critical magnetic field at 0 Kelvin, and so this is Tesla. So the magnetic field. So we know the critical magnetic field at 0 Kelvin. So the relation between the critical field between different temperature, it is critical field at temperature T is related to critical field at temperature 0 by this formula, by Tc square. Okay, where this Tc is the critical temperature at 0 Kelvin. Okay, so Tc is your critical temperature, which is actually 7 Kelvin. Tc is, you have to take 7 Kelvin. Now let us now what we have to, all we have to do is we just have to calculate this value. So for T we have to write T you have to put 2 Kelvin. T is equal to 2 Kelvin. And V0 we know what is V0. V0 is this value of put, and thereby we can obtain the critical field at T equal to 2 Kelvin. So if you put T equal to 2 Kelvin here, so all the values we know, we will obtain the critical magnetic field at 2 Kelvin. Then that we have to put here in this expression. So we know the critical magnetic field at 2 Kelvin. Mu naught we know, mu naught will have a value of mu naught equal to 4 pi into 10 to the power minus 7 in SI unit. So and thereby we will get the current. So let us try and do that. So our first step is to find the critical magnetic field at 2 Kelvin. So it will be V at T equal to 2 Kelvin is given by V at 0 equal to 1 minus T over Tc whole square. So this was 800 into 10 to the power minus 4 Tesla, and this is 1 minus 2 Kelvin over 7 Kelvin. So this in Tesla. So this will give us, if we calculate it, this is equal to 3 into 10 to the power minus 2 Tesla. Now we know that it is the R equal to V. So this we have to put it here. 1.35 into 10 to the power minus 2. So I is equal to this V into 2 pi R over mu 0. V is 7.35 into 10 to the power minus 2 into 2 into 3.41. This is R is equal to 0.5 Newton. So it is 5 millimeter. So it is 5 into 10 to the power minus 2 meter divided by 4 power into 10 to the power minus 7. So this should be in ampere. So what you get now is, so after this calculation, this will be equal to 1.37 ampere. So this is how you calculate your so it will be as this. So this is how you find your critical current. Now let us go to the next question. Landau-Ginzburg parameter kappa, it is this parameter is defined as lambda L over n S. This is the penetration depth or penetration length, and this is coherent length. So for type 1 superconductor, we'll have this penetration depth is penetration. So this kappa, it turns out to be less than 1 by square root of 2. And for type 2, this kappa, it turns out to be less than, greater than 1 by square root of 2. So this you get from the Landau method. Now let's come to the third question. So you've been given the binding energy for the Cooper pair, which is this epsilon equal to 2 h bar omega d 1 minus exponential of 2 over lambda. So what we have now is we have to, so no, lambda is a constant and lambda is less than 1. So now if lambda is less than 1, that implies that 2 by lambda is very greater than, so it is a very small number, so that is why 2 by lambda has to be a really very big number. So this implies that e to the power 2 by lambda is really very big than 1. This will be a much larger number. So if you try to if you subtract, so 1 is very insignificant as compared to 2 to the power lambda. So what we can write is epsilon is equal to 2 h bar omega d 1 minus e to the power 2 by lambda. So this is a very big number. So big that we can neglect 1 as compared to this. Or we can also say that if this is very big, e to the power minus 2 by lambda is a very small number. So 2 h bar omega t e to the power minus 2 by lambda is equal to minus 2 by lambda minus 1. So this is a very small number. So this gets, so we can simply neglect this and we have this minus 1 factor. So it is minus 2 h bar omega d e to the power minus 2 by lambda. So it is, this would be your correct answer. Now let us come to the next question. Choose the correct statement regarding the BCS wave function. Okay, the BCS wave function is, so the BCS wave function is an eigenstate of the number operator. So this is not true. And So let us first see what is the BCS wave function. The BCS wave function is product of. So the BCS wave function is actually product of these uh, all these states. So zero represents that the Cooper pair is uh, absent, and one represents that there is a Cooper pair. So since this is the BCS wave function, you can immediately say that this is also not true. So this statement is wrong, and BCS wave function is not an eigenstate of the phase. So this is false. It is an eigenstate of the phase. And the number of pairs can be fixed by integrating over the pairs. So this statement is true. So now let's come to the next question. Which of the following is correct pairing symmetry for the S wave superconductors? See S wave. So whenever you have uh, this S wave, so it is like a spherical wave with uh, so you know the spherical harmonics like S wave, P wave, and so on. So for S equal to 0, it represents the so 0 represents the S wave. For it, L is equal to 0. The angular momentum L has to be 0. So so why is this necessary? Because uh, so as to follow the Meissner effect, it has to be satisfied. That is why we need S equal to 0 as well as L is equal to 0. Now let us come to the sixth question. Which of the following expression explains the isotope effect in the BCS superconductor? So, according to BCS superconductors, so the critical temperature T is directly proportional to m to the power 1 by 2, where m is the mass of isotope. So, which means that Tc is inversely proportional to some power of m. So, Now let us come to the next question. Which of the following statement is valid for phonons? So phonons are, these are nothing but quantum of lattice vibration. So they are uh, so these are actually bosons, and hence they obey Bose-Einstein statistics. So this statement is true. So since they are bosons, they will have an integral spin. So only fermions can have spin-half particles. So this statement is true. Now the momentum of this is given by phonons is given by it can be inferred from the dispersion relation. So which is usually like if I want to plot for a 2 dimension like a lattice with this kind of lattice, so it will have some this kind of relation. Or if it is a lattice with just a single type of, like this is for 1D lattice, so it will have this kind of. So this is K and this is E of K. This K represents the momentum or momentum F bar K is equal to momentum. So this is clearly not, whereas here what it is saying is the momentum P is equal to H mu by C. So this is H bar omega, H bar K, and this is H bar omega by C. So omega is equal to K C, which is not. So this is, if you plot this, it is just a linear plot. Okay, K and omega, and the slope is C, so which is not the same as this. So that is why they don't have this momentum. This is correct for length. This statement is. So here the last option is saying it represents the vibration of individual atoms in a solid. So it doesn't represent the vibration of individual atoms. It is representing the vibrational modes of the lattice. So lattice means it will tell how all the atoms in the lattice they are oscillating as a whole. Yeah. So it is, this statement is wrong. It is not individual. Let us now come to the next question. Which of the following is false about the physics superconducting? The superconducting properties can be destroyed by application of the magnetic and electric field. So this statement is correct. If you apply too much magnetic field, then what happens? That Masonier effect. So there is some critical magnetic field. So at some temperature T and S, so Tc, and this corresponds to the critical field. So this is your superconducting state, and this is your normal state. Okay. So for a temperature T less than, so T which is less than Tc, there will be up to some critical field which will be superconducting, and after that it will no more be superconducting. This relationship this is given by Hc at T is Hc at T equal to 0 1 minus T over Tc whole square. Okay. So what we have is then the current, the electrons will, too much of electrons or electron current will be there, because J is equal to sigma E. Okay, as sigma goes to so as electric field will increase, the current will increase. But if the current will increase beyond a certain value, then this magnetic field will, so because of this current, there is a magnetic field just near to it. And that magnetic field, when it reaches above the critical field, then it will destroy the uh, superconducting nature, and you will have a normal state again. So application of high magnetic and electric field can destroy the superconducting property. The transition temperature varies as the atom is substituted by its isotope. So this statement is also correct, because experimentally it has been found, and it has been uh, like predicted by Mrs. Curie and all, that it is inversely the transition temperature or the critical temperature is inversely proportional to the square root of the mass of the isotope of that particular material. So the transition temperature is varies, that is why it is true. The variations of critical temperature is given by Tc is inversely proportional to m. So this statement is wrong. It has to be inversely proportional to the square root of m, where m is the mass of the atom. The elastic properties, the crystal structure, and the thermal expansion remain constant as the system becomes superconducting. This statement is totally correct. So mostly what happens is the uh, becoming a superconductor, it is a phenomena which is related to the availability of electrons. The electrons and how and its interaction with the lattice. So and that interaction can be really very weak interaction. So it doesn't, and the elastic properties, the crystal structure, thermal expansion, these are mostly determined by the crystal structure. So, and since that crystal structure is not that much affected, so all these properties doesn't change significantly. So this statement is correct. So they remain constant. Now come to the next question. The critical current which can flow through a long thin superconducting wire of diameter 1 millimeter whose critical magnetic field, okay, so critical magnetic field is already given and the radius is given. We just have to find the current. So we just have to find the critical current, and we know the formula. It is simply, so here we have to look at the unit. So this is that of the magnetizing field. 7.9 into 10 to the power 3 per meter, and this Hc is equal to R over 2 over R. So the current will be equal to Hc into 2 by R, and it is 7.9 into 10 to the power 3 into 2 into pi into R is 0.5. So it is just 1 by 2 and 4 minus 3 meters. So I am converting, say R is equal to 1 and 9 by 2, which is 0.5 meter. So this, if you calculate this, it will come up in ampere. So that is just this. So we have to calculate, and it will give you, okay. Now let us come to the last question. If the finite momentum DC state remember. So this is your finite momentum BCS state, and the energy gap is defined by this. So we have to find the energy gap, and we have to determine if it is dependent on this K or not. So how do we do that? So we have to find, so the energy gap delta K is given. Delta K, it is given as V, and sum over all the momentum states, and we have to take the average of this quantity, C minus K plus capital K by 2 now in C K plus capital K by 2 of C, and we have to take average of this. So average of these operators with which state? The state given is omega k, which is nothing but this uk plus vk c dagger k capital K by 2 of c dagger minus k plus capital K by 2 down, and this operating on the zero state. So now let us find this quantity. So delta K is equal to V over K. So we have to substitute this over. So there are these two cat would be so bra and cat would be there. We have to substitute this. So for this, what we have is UK. Now, since we are taking the conjugate of this, so this UK is a complex number. Okay. So it was dagger. So the dagger will be removed. We are taking a machine conjugate of that. And then write this quantity C minus K plus K by 2 down, K plus K by 2 up. Now we have to choose only those quantities which will survive. So let us ask ourselves which quantity will survive. So those quantities in which, so first note that there will be terms in which there will be so there will be terms in which there will be equal number of C daggers and equal number of C. Those quantities will be surviving because it will finally become uh, an eigenset of the number operator. Now, if you see, if you have a quantity in which there are more number of C than the C daggers, then those quantities will vanish. So only those quantities. So we have to choose. We have to choose only those quantities in which there will be same number of C and same number of C daggers. So what we have is G sum over K. You see, if this UK, so there is no C. If this gets multiplied with, we will have some quantity like. So this quantity. So from so these getting multiplied with, so this has to get multiplied anyway. So we have 2C already. Then we have to look for C daggers. So this quantity, so first it will go to two states up, so two particles of this momentum and spin will be created, and then they will be annihilated back again to this zero state. So this will give you uk e minus k plus k by 2 divided e k plus k by 2 and this, and there will be this vk I'm writing here k plus k by 2 up e divided minus k plus k by 2 down. Okay, so this is one term and this can be substituted. Now if you look what will happen to the other terms, so what are the possible other terms? Let's say we multiply, so first it gets multiplied with this, and we took this term from this last factor. What would happen if we had taken this term from the last factor? So after this operator has been, so there are these three operators we are dealing with. This is an operator, then this operator, and this operator. And we took this term from this operator. Let us say we are taking this term, this, so this term, and then this term. So after this, so after passing through these many terms, when it will operate with this, so this is an annihilation operator. This annihilation operator that will annihilate this zero state, and you will get zero. So what would happen if we had taken this? If we had taken this, then uk and then uk into zero get, this zero get when it get operated with here, it will again get annihilated. So the only term you get is this. Now in this you see there is C, here you see from here you have one annihilation operator and the creation operator. So what you will get is, so if you have an annihilation and creator, so I will just try to explain with a normal example. If we try to so we have this, this is the annihilation operator and this is creation operator, and if you take the commutator of the two, it gives 1. So this is a known relation. So C dagger minus C dagger C is equal to 1. Now you want to take the average of that, of C dagger is equal to, so C dagger from here it will be 1 plus C dagger C. Okay, so is C dagger so now we will have two terms. For the first term, this C will annihilate this, so all you have is this, which is equal to 1. So only with this you will have a non-zero term, but yeah, so that is why, and it is just a number, right? So what you have it from here is, so so these two, it will give you the same status. Uh, so these two will be independent of. So when you operate this will be independent of this k vector, because as you saw here, it is independent of the. So it will just give you a number, and it is independent of momentum or anything. So here you see it will, this term will be independent of the momentum, and then you will be left with this and this. That again will be independent of the momentum. So what you have is you will just have this v sum over k u k v k, and this 0 0 it is just 1. So this thing is independent of that k. Independent of capital K. So these are the questions this uh, for this week. Let us look for some of the questions of the next week, of the previous year question. So choose the correct option regarding the following statements. So qubits, what are qubits? Qubits are nothing but quantum bits. So what it means is, so for example, so there would be states like this. These are quantum states, and in these states they are encoded with information. For example, you can say that this 0 can be the spin down state, 1 can be the spin up state, and any superposition of them can also be a qubit. So so now in a bit what happens, the memory is stored in either 0 or 1. Here now you have the superposition of this 0 cat and 1 cat and all the superpositions in between. So you can, so uh, A 0 plus B 1 and A square plus B square. So you can change this A and B, or what you can also write is A 0 plus 1 minus A square B. And so this A can be any value from 0 to 1. Okay. So there are infinitely many values, and so that is why you have, it can store more memory than bits. So this is a correct statement. Qubit can store as much memory as we want. So this is, so this is also true because we have infinitely large number of the qubits. If there are n qubits in a quantum computer, then it will have n square different state. So this is not true. Not true. For so for example, let us say we have two qubits. So 0 and so these two qubits can be 0 1 or 0 1. So, or this qubit also can, this is the first qubit, second qubit. This also can have this. So if you have two qubits, then the possible number of states that is possible is 0 0 0 1 1 0 or 1 1. And so from this you can build up any linear combination of the states. So but from this, how many different states we can make is, it 2 to the power n states. So this is wrong. Quantum computers could help us in cryptography and data security. So this is true, and hence there are large number of research going on this quantum cryptography, security and all. So this statement is correct, wrong. And so B and D are correct. Here what it has given is, in the second question, the critical field for niobium is critical field here, it is ampere per meter, so we have to take as C is equal to n into 10 to the power 5 ampere per meter, and at 8 Kelvin, and at absolute zero, at T equal to 0 K, at C 0 is equal to 2 into 10 to the power 5 ampere per meter. So find the value of n if the transition temperature is, so Tc is given as 11.3 Kelvin. Here you have to use again that relation. Hc at T is given by Hc at 0 1 minus T over T. Okay. So what you have is Hc of 0 is 2 into 10 to the power 5, 1 minus T square is 8, and this is 11.3 whole square, and this is n into 10 to the power 5. So n will be 2 into 1 minus 8 over 11.3 whole square, which is almost equal to 64, and this is 7.4, almost 128. So this is 2 by 2 approximately 1 to 1. So the value of n is equal to 1, almost equal to 1. Now let us go to the next question. Which of the following is true regarding the case of BCS wave function and the number of occupied states? So this relation from BCS theory, it comes as delta n delta phi, it is greater than or equal to 1. So this is the correct answer, the rest all are not to measure very tiny magnetic fields, which of the following instruments is most useful? So to measure very tiny magnetic fields, we use something called squid. So what this squid is, so it works on the principle of superconductivity. So it is actually superconducting quantum interference. It is very sensitive to very minute magnetic fields. So here the variation of critical temperature with atomic mass for a VCS superconductor Tc is directly proportional to, we know that, square root over m. So which is nothing but Tc is directly proportional to 1 by m to the power 1 by 2, and Tc directly proportional to m to the power minus 1 by 2. So alpha is equal to minus 1 by 2. So this is your correct answer. A Josephson junction operating at an AC frequency has a voltage of n microvolt across its terminals. What is the value of n? So this the way we have to solve this question is, so the frequency is given by, for Josephson junction for association. So the frequency is given by QV, which is your energy. So if this is your voltage, then this is the energy that you need to give, and the frequency is h nu. Now the voltage you have to apply for a superconductor. Q is equal to 2A, because this uh, there uh, there will be two electrons in a Cooper pair, and from here what you can do is the frequency is QV over h. So therefore this will be 2EV over h, and the voltage across terminals, voltage, that's mu over 2E. So we have to solve for this particular voltage, and mu we know, and the charge we know. So we just have to put all the values. V is equal to 6.626 minus 34, mu is equal to 482.9, 10 to the power 6, to E is 1.625 minus 19, which will give you, if you solve for this, you will get something around 1. So in this question, neodymium wire of certain radius is given, 0.25 millimeter is the radius, and it it has already given the current I is equal to 300 ampere, and what is it is just asking what is the magnetic field inside the current carrying wire. So all you have to do is B equal to mu 0 I over 2 pi r. Okay, so so this is all you need to do. So it is 4 pi into 10 to the power minus 7 into I is 300 ampere and 2 pi, and radius is 0.25 into 10 to the power minus 3 meter. So this is your magnetic field inside the current carrying wire. In gaseous theory, two electrons form a Cooper pair such that such pairs condense to form superconducting state. Which of the following statements is true about the gaseous ground state? The gaseous ground state, it is an eigenstate of number operator. This statement is false. It has a definite phase. Uh, this since gaseous ground state is an eigenfunction of the phase, so it has a definite phase. The partners are in a pair very close to each other in space. So this statement is false. Why? Because they are actually retarded. Suppose, for example, one electron will come here, then because of this attraction of electrons, this uh, this lattice points, let's say these are the lattice points, they will come closer as compared to the other lattice points. Let's say here, they have come closer because of this attraction. Then as they will this electron will go away, it will take some time for this nuclei to relax back. So when the other low energy electrons will come, it will get attracted by this uh, lattice, which is a small positive charge. So what will happen is they will. So this is like in the space, in the spatial dimension, these two electrons can be really very far. It is the effect of this electron which this electron will see. the net momentum of this has to be 0. So this statement is also wrong. So your correct answer is this. Determine the temperature at which the critical field becomes half of the value at 0 K. So this we have the relation. The critical field at temperature T is critical field at temperature 0, 1 minus T over Tc square. Okay. So we want we want to find the temperature at which this is exactly half the value at this. So we just substitute this value here. So Hc0 by 2 is equal to Hc0 1 minus T square over Tc square. So what we have is this will cancel 1 by 2 into 1 minus T square over Tc square. So T square over Tc square is equal to 1 minus 1 by 2 equal to 1 by 2. So this will give me T square equal to Tc square by 2, which will give T equal to Tc by square root of 2. So this is the correct answer. Now let us go to this question. Which of the following is true about the topological insulators? So they have conducting states in which interior value surface no the topological insulators are say on the surface they will be conducting, and these surface states are symmetry protected. Okay, and the edge states they occur in no so and the edge states they will occur, occur in oppositely propagating pairs. So along one edge, if they are propagating along this direction, the other edge they will be propagating along this. And the time invariance is it is preserved in case of the topological insulator. So this statement is wrong. The edge states they propagate opposite, and it is only at the surface that the topological and in the bulk it is insulating, but at the surface it is conducting. So this statement is wrong. So the true statement is this. So these are the questions we have to discuss this time. If you have any other questions,